to be providing the free courses on the weekly basis. Okay, so that I try to contribute to the community as much as I can. Okay, so for today we are going to be actually be looking at the CFX, because CFX is like uh, any questions? The CFX is like a not very well known software to the many people. Many people they use the Fluent, and they have the good idea, and it's easy to use actually the Fluent. So my idea is that to give the knowledge or the basic understanding how the CFX works. Okay, so now you can work on the CFX in two ways, either from Workbench, or you can start directly from the start menu. And I'm starting from directly from the start menu, and you will see that there are the four options on the top of the menu. One is the turbo kit that is used for making the meshing for the any turbo machinery, turbines, compressors, pumps. CFX Pre. So unlike the Fluent has the single environment. And secondly, the Fluent works on the basic working principle of the Fluent is that it works on the control volume. So what is control volume? I'm drawing the two-dimensional grid. Okay, so I will not go into the more theory about the control volume or finite volume. So it has the cell structures, and we have the cell centers, and on the corners we have some separate treatment, and they are divided into the like a north, south, east, and west faces, and we have the cell nodes and the vertices. So whatever mesh you produce yourself, that mesh will be used by the Fluent. Also, okay, so maybe you are wondering that the it's not a big deal that the whatever mesh we generate that will be used by the Fluent, but actually this is the a different scenario in the CFX. In CFX, what happens? For example, in the Fluent, I have the mesh that is having the hexa elements or prism elements in the near to the wall, and away from the wall, let's say we have three layers of the boundary layer mesh on the wall, and then we have the tetra elements as we are progressing along the core of the domain. So now what happens here in the CFX is that the CFX will create its own mesh from the our mesh that we are going to provide from meshing software. For example, now the cell nodes for triangular elements, they will be here. Okay. So what will happen with the CFX is that it will be creating the mesh like from these nodes. So now the element that is generated by the shape functions inside the CFX is now this element. So instead of having the tetra and the hexa elements, this is going to be the polyhedra. Okay, and this is the reason that the CFX does not like the polyhedra elements. Okay, and secondly, CFX does not allow you to use the dynamic meshing. Why? Because it has a very peculiar element types that are not suitable for dynamic meshing. Okay, so dynamic meshing is not allowed in CFX, although you have the option to like stretch the elements by having the same element shapes. You can stretch them this line can be elongated here, but that's all. You cannot regenerate and make the new elements and try all elements like you do in the Fluent, because it has like a very different element shapes that are generated, not the original one that we have provided in the mesh. So, and that's also reason that the CFX results are more accurate because it is using the high order elements. And thirdly, it has a more convergence speed because it uses a fewer elements, because now it creates like a, from the 1 2 3 4 5 like a 1 2 3 4 5 from five elements, it made the only one element. So mesh size, although you are giving maybe 5 million, but the mesh that will be used by the CFX may be around 1.1 to the 1.5 millions. Okay, that's why it is generally speaking it's faster than the Fluent. Okay, but the problem is that the CFX has a like a separate apps for the pre-processing, the solver, and then the CFD post. So let's open the CFX Pre. And before you open, you can also set the working directory that is provided here. Okay. So from here, you can provide your own working directory. For example, if I go to my computer here, let's say I want to open the some case. So I have already mesh done in the some software. So let's try to have the that case. Okay. So I'm leaning towards the typical case of the pipe. So I'm going to the using the pipe case. So I will use now CFX can open the different meshes. It can open the ICM CFD mesh. It can open the Fluent mesh also. It can open the its own mesh that's having the extension of the CFX5. And also you can directly open the CFX PD file as well. Okay. So here, pipe flow. Okay, so I can use the Fluent and ICM CFD files. So let's choose this working folder. Okay. Now, if I use a new working folder, so I have to open the CFX Pre. So this will now refer directly to the working folder. Okay. And second shortcoming is that one is like it has a difficult interface and different software for the for pre-processing, processing, and then the CFD post. Secondly, when you import the mesh, okay, when you import the mesh, what can you cannot provide is that you cannot provide the name selections or the boundary conditions to the software. Okay. So CFX, but definitely you have to define the name selection so that they can have the separate boundaries, and that you will define in the CFX Pre. So name selections or the boundary condition types will not be defined prior to opening into the CFX Pre. That will be done inside the CFX. Okay. And secondly, thirdly, the interface is very like a very like a boring. Maybe you can call the interface. It's not a as intuitive like a Fluent, but you can like start to work and it will start to appear more and more to you. Okay, so for example, if you click on the new case, so now we have the four options: the general, turbo machinery, quick setup, or you can open the library template, or you can also make your own library template. So let's say we are with the only are going with the general tab. Okay. Okay, so now we have the options available here. First, we have to import the mesh. So right click here and click on the import mesh. So you can import the CFX mesh that is having the like a format that is the GTM. GTM is for turbo machinery from the turbo grid, and CFX is a default format. And if you open the ICM CFD format, that is a CFX5. Okay, old one they can have the CFX, but now they have the CFX5 and also the mesh file .msh. Okay. One more thing that I want to point out here is that the CFX don't have the any 2D version. Okay, so no 2D version, it only works in the 3D. So now question is that how we can work on 2D cases. Definitely we have the 2D cases like we do in the Fluent. So for 2D case, what will happen is that if you provide the planar geometry, for example, the flat plate, okay, so then it will ask you that to provide the thickness, some thickness, and that will be used to actually make the 3D geometry. So you can provide the unit thickness like a if the geometry of the plate is like maybe it's 10 meters, you can provide the 1 meter thickness. Okay. And it will create the mesh, 3D mesh automatically. So you don't need to create 3D mesh yourself. Just import the fluent.msh file and it will extrude the file by the 1 unit depth. Okay. For the axisymmetric cases, for example, cylindrical cases, in that case, you have to provide the only half of the plane area. For example, it's a cylinder. Okay. And you just need to create the one plane from center to the top wall. Okay. So provide that location, that mesh, plane, the half mesh, half plane mesh, and it will extrude. You can provide the angles, it can extrude by the 5 degrees. 5 degrees would be enough. Okay. So for the axisymmetric meshes, you have to provide the 5 degrees maximum. And for the two-dimensional planar meshes, you have to provide the 1 unit depth. And it will create the mesh by itself. Okay. So don't need to worry about the 3D meshing creation by yourself. Okay. So now what I'm going to do is that I'm going to import the ICM CFD mesh file. Okay. ICM CFD mesh file are the simple fluent mesh file. And secondly, you should be careful that the units you are providing, they should be correct. If the mesh was generated in the millimeters, then you have to provide the millimeters. If it was in the feet, have to provide the foot or meters. So right now it's a meter, and I'm going to use the medium mesh. Okay, so 1 minute. Okay. Okay, so you can see that we have the now pipe is displayed on the screen. It's a gray color, but if you go to the meshing and click on the mesh, you will see that the mesh will appear. Okay, this is a pure hexa meshing, and it was created in the ICM CFD. Although we have the also ICM CFD file, we can open from there. And if you double click on any surface, for example here, then you can change the properties. Okay, for example, you can change the lightings here. Okay, you can change the line colors, you can change the visibility of the like a draw lines. And you can change the transparency to the like a 0. Okay, now it's not transparent and you cannot see from inside. Okay, you cannot see through. Okay, so again, if you change the shading to the transparency to the 50% around. Okay, now you can see from inside. Okay, you can change the many parameters here. Okay, so now we have the three regions, not the boundary conditions, but three regions. So now to provide the boundary conditions here, what you can do is that you can go to flow analysis, right click here and insert the domain. Okay. So default domain is already there. So don't need to put the domain here. If there are two domains, for example, for turbo machinery, we have the two domains for stationary and the rotating, then you can put them in this way, but that should be inside the over here, subdomains. Okay. So now we have the boundary. So let's put the name as the inlet. Okay. So I will select the inlet. Now this is the inlet region, not the boundary condition. Okay. Boundary condition is now we are providing here. So this is the inlet region here that is selected in the green color. And boundary details. So this is going to be the velocity inlet. So I'm going to provide the velocity as a 1 meter per second. Okay. Then the second one is that I have to provide the second boundary, and that boundary is the outlet. On the outlet, we don't need to provide any condition. Only the zero pressure will be enough. Zero gauge pressure. Okay. Apply. And the third boundary condition is going to be the wall condition, that is cylindrical wall. Okay. So that's the wall. And we will choose the cylinder wall as the boundary condition. Okay. Okay, so now we have defined the three boundary conditions here. Now the next thing is that we have to define the material properties. Okay, so what material properties I am planning here? I am planning here the some flow conditions that I will show you. Okay, Okay, I'm trying to find out the slides that will be used for the boundary conditions. Okay, so yes, here. So what boundary conditions we are going to provide? The velocity is 1 meter per second, Reynolds number is 100, viscosity is 2 into 10 power minus 3, and the density is a 1 kilogram per meter cube. Okay, and the length and the diameter are given already there. If you want to confirm, that you can confirm from the scale here. Okay. So this scale can be used as a roughly tool. Okay, you cannot have the precise dimension, but you can use it roughly. So this is equal to 8 meters. Okay. Now to get the diameter of idea, you can take the second, the circular face, and then use your mouse middle button. There's a wheel there, and just keep on zooming. Okay. So, so this is approximately the 2 meter, zero point 0.2 meters. Okay. This is same as shown over here. 0.2 meters diameter and the length is equal to 8 meters. Okay. So now next thing is that you have to provide the material properties. So here you can see there are the different material properties already there. Water ideal gas, air at 25 degrees Celsius, air ideal gas. So these are already there and you can actually create your own material as well. So you can insert material and let's say I put the name as a my material. Okay. So molar mass you can keep any value and the density is equal to the 1 meter 1 kilogram per meter cube. Viscosity is 0.002. Okay. Transport properties 0.002. Okay. One more thing is that units here, they are given as the Pascal second. Okay. And units here are provided, they are the kilogram per meter second. Okay. Kilogram per meter per second. Okay. That you can also kilogram per meter per second. And you will see that they have the same values because they are exactly same values. One is like a primary unit and one is the other secondary unit. So from Pascal, Pascal is Newton per meter square. From Newton, Newton has a definition of kilogram meter per second square. If you simplify them, you will get these units. Okay. So going with the Pascal second or kilogram per meter per second is the same thing. Okay. So we have defined the properties here. Okay, now let's go to the here. Now you can see that we have the fluid one. Okay, so in the fluid one, what you have to see, what you have to do is that you have to provide your own material that we created in the panel there. Okay, that is only we have defined the material. Now, which material will be used by the our fluid that is for the pipe is going to be defined from here. Okay, so reference pressure is a 1 atmosphere, which is same as a 101325. It's a non-buoyant flow. It's there's no viscosity, density effects are there. Domain is not moving. It's a stationary. Only flow is moving with the velocity, given velocity, and no mesh deformation is given here. Okay. In the fluid models, we have the isothermal. That's okay. And we have to choose none. Laminar flow is there because Reynolds number is less than 2300, so it's a laminar flow and you can keep it as isothermal or you can keep it none because there's no heat transfer is involved there, so you can make it none. And you can initialize from some value, but you can just leave as it is. Okay. Okay, so we have defined everything there. Now come to solver control. I'm going to reduce the convergence criteria to 10 power minus 3. And also I want to make the mass flow rate convergence criteria to the point 001. Okay. And click on OK. Apply then OK. And maximum iteration, you can change them to the 200 and click on the OK. Okay, next thing is that you can output something here. For example, here you can have the monitors. Okay. So by default, we have the monitors for the continuity, momentum equation, and turbulence was there. Then turbulence will be there. But you can also create your own monitor points. Okay. For example, you can measure the pressure value, you can measure the flow rate, you can measure the velocity on different locations. Okay. So here, these are all parameters you can monitor. Okay, now click on OK. Okay, the last thing would be that if we are here, then maybe we have to like okay, so equation settings is there. Okay, this is okay. Dynamic mesh, dynamic model is not required. Advanced options is that we have to okay body okay, we don't need to do anything at all. So now you can save the file. Okay, so I'm going to save the file in some other folder. Okay, so rename. It is not allowing. Fluent does allow the like with the spaces. You have to put the minus sign, hyphen sign, and then you can go. Okay. So the object turbulence present in the object that is in the boundary condition, but it's not physically valid. So because turbulence was turned off, so you have to go there and just confirm that do we have any boundary condition for turbulence. If not, then you can again click on OK. Okay, now this error is now disappeared. Okay. Okay, so any questions? Any questions? You can put the many things here. Okay, so now I saved the file. Now next thing is that you have to output the file for the solver. So you can go to solve and define run. The second is that the run solver and monitor. Okay, here you can directly like define the run and it will like save the first file like this. Okay, now it will open the CFX solver. Okay, so here you have the like options. So this type of one is like full yes means full means that it will be solving the case, and other option is that only for partitioning. Okay, initial values you can specify the initial values by yourself. Okay, or you can just keep the default values. Okay. Okay, next thing is that you can like put the like a parallel solver. So let's say now if I put the Intel MPI local parallel, so I have the 4 cores, I can define the 4 cores here. Okay. And for large problem with having the like very high mesh or you want to go for double precision, you can turn on these options. Okay, now start the solver. Okay, here you can right click and you can click on the switch residual mode. So this will be like maximum, or you can go for the average. Okay, or root mean square. Secondly, if you right click here on monitor properties, you can go to range settings and you can like uncheck the set manual scale. Okay, so now it will be inside the your scale here. Okay, so why the solution has stopped here? Because you can see the message. If you go upward, so all target criteria had been reached. Okay, if this is reached, then it will stop before the number of iterations. Okay, if you want to run for this case for the more iterations, so what we have the options here, you can like close the solver and put the more zeros here. Okay, like a 10 power minus 8. And for the mass flow convergence, maybe you can put 10 power minus 4. Okay, click on OK, save the file, and again start solver, define the run. Now this will override the old file, and you can allow the MPI options. Okay. Any questions? Okay, one more thing is that actually, if you take a look here, you have the many options. Okay, you can edit the settings here. You can stop solution from here as well. Okay, you can create a backup of the your case. Okay, so now it is like almost converged, so we can stop here. Okay. So once the file is stopped, like unlike the Fluent, as I told you that the CFX has a three softwares, CFX pre for pre-processing, solver for solving, and the third one CFD post. And CFD post was actually its name was CFX post. Now, after buying by the ANSYS, they changed the name from CFX post to the CFD post. Now it can be also used for the Fluent as well. Okay. So now you have to click on the post-process results. So, and you can, if you want to shut down the solver, you can click on this option and then click on the OK. This will close the CFX solver and open the CFD post. Okay. Again, similar in a similar way, you can actually display the your geometry file. Okay. Okay. If not, you can open it from the CFD post here. Okay. I think we close the file maybe accidentally. Okay, now you have to look for the result file. So where the file will be in the working folder. Okay. Okay, so I guess we have closed the file. Okay, so let's go again from the solver. Okay, we have the file saved in the some other folder. That is like from where we actually loaded the file. Let me check. It's newer old files. So these are the new files. Yes. So what we can do is that we can actually copy these files. Okay. Yes, please.
Hello.
Yes.
I'm sorry I joined very late.
Okay.
I just saw the lecture. I noticed that people that do turbo machinery simulation prefer
Yes.
CFS
Yes.
over Fluent.
Yes. True.
What is the advantage?
It has like a lot of options that are not available in the in the Fluent. For example, transient simulation. There are two options I don't remember, but like there's a phase change, means that you can only solve the one component and still you'll be getting the effects of the transient solver. Okay, unsteady simulation that is not possible in the Fluent. So these are the benefits actually.
Okay.
So for that, I can give some extra classes some at some time if you want. Okay. Okay. So here I'm going to copy the file in the folder here. Okay. The files were actually saved there. Okay. So here now I can open the CFX post directly and point to the proper directory. Okay. So you should be having the proper directory already pointed. Okay, so I'm going to load the results and where this is going to be F and the CFX course. Okay, so two files are made. First file was made when we stop the file first time. Second file is made when we stop the file second time. Okay, every time they will put the same name but underscore 001, 002, 003 like that. Okay, and RE stands for result file. Okay, D stand for definition file for the CFX solver. Okay, so you can display the wall, and if you double click, you can actually change the properties. For example, you can show the mesh lines. You can change the colors also of the mesh lines. Okay. So for every boundary condition, you have to you have to click on the tick mark and then double click there and open the panel, and then you can change the properties. This is inlet is on this side. Okay, so now I'm going to make a one plane iso surface, and that will be on the constant x or constant y, because the x and y, they will provide you the center plane. Okay, so choose the constant x and apply, hide the wall. Okay, so we have the isosurface 1. I'm going to hide the isosurface and I'm going to create the pressure contours on this surface. Isosurface 1 and pressure values will be local, and click on the OK. Okay, so you can see the pressure is varying from inlet to outlet. So on the inlet, the pressure is highest, that is 13.65 Pascal. This is the same, it is confirming by the theory also. Same I have determined through the pipe theory. Okay, this is through the pipe theory. This is through pipe theory, okay, through the simple formula. So this formula pressure is 12.8. Why the 12.8 in the theory and the CF and the CFD is at 13 point something? Because the theory does not consider the any developing region, but in the CFD, what is happening is that some region is developing region, and that is not counted for in the theoretical formulas. That's why there's difference there of the some value like a 10 to 8%. But that's okay. Okay, so it is confirming that our results are confirming to the well-known pipe theory. Secondly, you can plot the velocity vectors. So again, isosurface, you have to hide the vector plots, and now the contour plots. Now you can display the vector plots. They are confirming that we have the parabolic velocity profile. It is showing the parabolic velocity profile. So if I reduce the, if I go to the you can change the put the here. Okay, this is okay. In the symbol, if you change the scale to the 0.1 initially, okay, color should be okay. This is okay, and make it local color. Okay, symbol size, make it like a 0.2. So you can see this is confirming to the known theory that we have the in the pipe we have the velocity vectors. They actually follow the parabolic velocity profile. At the center, velocity will be maximum, and that velocity will be equal to the twice the velocity we are putting at the inlet. That is the average velocity, 1 meter per second. So if you multiply with the 2, you will get the 2. So you can see from a scale that we are getting 2 meter per second in the center. Okay. So now this is the end of the class. And any questions? Any questions? Okay, thank you. Thank you. See you again next week on some other courses.
Thank you.
Okay, bye bye.